Hello.
Hello, nice to see you.
Good afternoon.
Good afternoon, guys. Nice to see you. Hi. Okay, so I guess you have received already my email as reminder about our midterm tomorrow. It will be the third midterm. All topics from uh, chapters which were not covered previously until the end of mechanics. So this topic from started of thermodynamics and molecular physics will not be included as only mechanics until the end. So these topics related to thermodynamics and molecular physics will be included in the final exam, where, I mean, everything will be included, but including these last topics. Okay, so please be careful with your answers. Don't make problems first, and then define those which you can easily solve. Afterwards, solve them and spend time on figuring out other problems which are not clear from the first point of view. Also book in logging into the system prior the deadline in time, so at least 15-20 minutes before, to be sure that there are no technical issues with logging into the on-campus system. Nothing new. Everything is the same as you did before. So I hope there should not be any technical issues with this midterm. Okay, so last time we continued our discussion of molecular thermodynamics and molecular physics. In particular, we introduced main processes and related to ideal gas. Also, based on these experimental empirical results, we obtained the equation for the state of ideal gas and presented in two different formats. So one when we use number of moles, and another when we deal with the total number of particles, atoms, for instance, comprised by the volume where this ideal gas is considered. So in first case, we introduced a new constant R, which is a universal gas constant. And in the second case, we end up with new constant KB, which is Boltzmann constant, equals to R divided by NA, Avogadro's number. This constant is used when we deal with total number of atoms which creates a considered ideal gas. Okay, today we proceed further, and today we will talk about internal energy and heat. So that will be kind of the focus on our discussion today. We will define what's internal energy more clearly, and also heat and heat transfer, some also latent heat, which associated with phase transitions, not only with heating the matter, like increasing temperature. It could also require so-called latent heat to carry out the phase transition from solid to liquid, for instance, or from liquid to vapor state. Okay, so let me switch the camera. So we have our slides. Where is And if we consider some arbitrary shape body, then define its center of mass, then internal energy of this body will be defined by kinetic energy of translational, rotational, or vibrational motion of all atoms which form this body, and also potential energy of their interaction between each other. However, we need to specify that when we define this potential kinetic, this kinetic energy of translational, rotational, or vibrational motion, that should be considered with respect to some reference system, which originates at the center of mass and is stationary, so it doesn't move with respect to the body with respect to its center of mass. So that implies automatically that kinetic energy of the bulk of this body with respect to some ground or some other system of reference system will not be included into internal internal energy. So any translational, rotational, or vibrational energy of the bulk of this center of mass motion with respect to some other system of reference will not be considered as internal energy. So only this kinetic energy of atoms with respect to the stationary system of reference originated at the center of mass of this body. So, no, and of course, we need to add there, also need to consider potential energy of interaction between these atoms which form the body. So that is definition of internal energy. And also we need to introduce heat. So usually it's denoted as capital Q. So heat is defined as the transfer of energy through the boundary of a system because of some temperature difference of the system and its surrounding. So if we have some system, some, for instance, some cube, then we keep this temperature of the cube at certain temperature T1, and we have environment at certain temperature T2. Let's assume that T2 is larger than T1. Then through this external boundaries of the system, we will have some heat transfer Q proportional to the difference between the two temperatures, the temperature of the environment and temperature of the system, which we consider. So initially, heat transfer was considered in a model of a flow of some specific liquid called caloric. And that's where the units for heat are originating. So we use calories, usually L. And that was before we had a clear understanding between the relationship of mechanical work and heat. So since it was shown that we can convert mechanical work to heat, then there is no real need in considering any hypothetical fluid. So we can consider just the energy transfer, and the unit for that is joule. So we don't need to invent anything else. However, historically, we still have calories as unit for energy, and specific for heat, and is defined. So one calorie is defined as the amount of energy to be transferred to heat 1 gram of water from 14.5 to 15.5 degrees Celsius. So that's a definition of 1 calorie. And since there is a relationship like mechanical equivalent of heat, because we discovered that kinetical energy transforms into internal energy via friction, then we can also find the equivalent of 1 calorie in joules. So that is equal to 4.186 joule. So that gives us the amount of joule, which gives us 1 calorie. So in order to start dealing with heat transfer and amount of heat which is transferred to cool or heat some system, we need to introduce a parameter which will relate the amount of heat transfer with the change of temperature. So that is so-called heat capacity, usually marked as capital C. And we can write that amount of heat, Q, is equal to heat capacity times change in temperature. Since heat capacity does not, so it defines properties of the system as whole. So it means that it defines how much energy should be transferred to the system in order to change its temperature by 1, for instance, 1 degree Celsius. However, it does not underlines the unique features of the material from which this system consists. So that's why a very common approach is to operate with so-called specific heat capacity, and that is usually denoted as small c, which is equal to, can be defined as transferred energy, like heat, divided by mass of the system and temperature difference, delta T. So means that this Q can be given as specific heat capacitance times mass times delta T. So the difference between heat capacitance and specific heat capacitance tells us that specific heat capacitance defines the heat capacity per unit mass. So that already tells us more about the properties of the material this system consists of, because as we know, different materials possess different heat capacitance and like specific heat capacitance. And that's why here you already need to specify also amount of this material in terms of its mass in order to define the total heat capacitance of the system. So this amount of heat which is transferred, assuming that we consider some like solid state system which does not expand much, so it thermally expands when there is some increase of temperature. However, it's negligibly small expansion, and work done by atmosphere because of this thermal expansion of solids is negligibly a small amount. So we can assume that all this transferred heat becomes, so we can write here C times M delta T, is actually results in the change of internal energy of the system. So either we have positive change or negative change, depends either we increase temperature of the system or decrease by cooling it down. So another important thing what we need to highlight here, that specific heat capacitance is a function of temperature, means it's not constant, it changes as temperature changes, and it behaves differently for different materials. That's why when we have quite large change of temperature, delta T, in order to calculate accurately the transferred heat, we need to integrate. So that will be integral from T1 to T2. C, we can put M here out of integral, assuming that mass of the system doesn't change, specific heat capacitance times dt. So that when we have large change in temperature, in such temperature range where heat capacity, specific heat capacitance should be considered as already a function of temperature, then we need to integrate in order to get the correct amount of heat transfer. If we go to another slide, we can here mention that we need to also to consider conservation of energy. Means if we have two bodies which are in contact with each other, and there is a possibility for some heat transfer through their boundaries, and they are isolated from other like environment. Then amount of heat which receive cold body should be equal to minus amount of heat which was taken from the hot body. So that tells us that there is some conservation of energy. And if, for instance, we consider two systems, let's say we have M1, C1, T1. So we have mass of the system M1, specific capacitance C1, and it states a temperature T1 at initial condition. Then we have another system M2, C2, and T2, which with all these three parameters define the amount of energy, actually internal energy accumulated in the other system. Then when we put them together and we reach some final temperature, T final, which is thermal equilibrium temperature, then we can write the following equation. So we can write that M1, C1, T1, sorry, not T1, that should be already, we should take into account the final temperature. So it will be final temperature minus T1. So that shows how much heat was transferred to or from first body. And that should be equal to, let's assume that T2 is larger than T1, then system 1 will be heating up and system 2 will be cooling down. M2 times C2, and here will be T final minus T2. So based on this conservation of energy concept, we can define either final temperature, thermal equilibrium, or we can, if we know this final thermal equilibrium temperature, get some unknown parameters of these two systems. So now probably would be better to move to another slide so we have more space. We can put all things together on one slide. Let us consider some heating of ice, including into this process phase transitions, which will occur at certain temperature, and define at each interval of this process of heating piece of ice, how much heat is transferred. So to make it more visual, we will consider a plot. So here we will have energy in joules, like transferred to the system. So here will be temperature in degrees Celsius. So let us assume that here somewhere we have 0 degrees Celsius. So we will start, let's say, from minus 30 degrees Celsius. and we have certain mass of ice, mi, mass of ice, and we start to heat it up. So by transferring some energy to the system, its temperature starts to increase. So we can show it like this. Temperature increases until it reaches 0 degrees Celsius. At this point, phase transition of ice to water start to happen. So we need to introduce such term as latent heat. So we can, Q is equal to L, some coefficient which defines the system and type of phase transition which happens, times like delta M is mass of the system which have experienced this phase transition. So L is latent heat, which like specific latent heat per unit mass, which defines energy required for phase transition. For instance, the first phase transition, which we will consider in this example, that will be ice to water. So at this point, when we reach 0 degrees Celsius, the temperature, while energy still continues to be transferred to the system, will not change, will remain constant. Why? Because this energy will be converted into this latent heat in order to drive the phase transition. So here we can write that we have ice plus water. Once here at the beginning, we have only ice. So when we converted, like finished with this phase transition, and all ice is converted into water, then we have already water, and we can heat it up if we continue providing some energy to the system. So that will be something like this until, this will continue until we reach 100 degrees Celsius. So we consider this experiment to be carried out at the sea level. So water starts to boil at 100 degrees Celsius, and start to produce, starts phase transition, water to steam. So boiling is actually what is the difference between steam formation of hot water, which is still not boiling, and boiling water. So in boiling water, steam is produced from whole volume, as opposite to not boiling water when it's just hot, and because of some Boltzmann distribution, there are always some fast molecules, water molecules, which can escape and form this vapor on top of hot water. However, when we reach the phase transition, water to vapor means we reach the boiling point, then evaporation starts from whole volume, and not only from the surface, but also from the volume. That's why we see all these bubbles inside boiling water. And this phase transition will require also latent heat. which will be defined by a phase transition from water to vapor, like steam. So here we have water only, and this phase transition will happen at constant temperature. Temperature does not increase until all water is converted into steam. So here we have water plus steam. So that will continue until we convert all water to steam. Then, when we have only steam inside our system, we can further heat it up by transferring energy inside this system. So here we have already only steam, and we can heat it up. So there are no other phase transitions. Steam doesn't experience any phase transition upon heating. So we can heat the steam to extremely high temperature if we keep it in a sealed container. So actually, electric power stations, which doesn't matter, is it like some coal or nuclear power station, it all like active area of power station heats up water steam to extremely high temperatures, like about hundreds of degrees Celsius, and this hot steam is rotating turbines, which the shafts of which are connected to the rotors of electro generators and produce electricity. So that's quite common process in electricity generation to deal with extremely hot water steam. So now we can divide all these processes of heat transfer and change of temperature into different regions. Sorry. So we can consider region A, where we have only ice, region B, with some latent heat, Li means phase transition of ice into water. Then we have some region C, and here in the region A, we need to consider specific heat capacity of ice. Here, specific heat capacitance of water. Sorry, so this is segment C, and specific heat capacitance of water. Then we have latent heat of water to steam conversion. That will be region D. And here we have region E with specific heat capacitance of steam. So now we can quantify amount of energy which was like amount of heat which was transferred to the system during this process for each of these segments of on the plot. So let's say part A. So here let's mark QA, like now amount of heat associated with this region A will be equal to mass of ice times its specific heat capacity times delta T, change in temperature. So in this case, we have like T2 minus T1. So that should be 0 degrees Celsius minus 30 degrees Celsius. So that is our change in temperature. So we heat up this given amount of ice from minus 30 to 0 degrees Celsius. So then we consider part B. For part B, we have latent heat to be considered because we have phase transition. So we can write that QB is equal to latent heat Li of ice to water phase transition times Mi. We assume that we converted that all amount of ice experiences phase transition. So we don't need to define here any temperature difference because temperature doesn't change. It remains constant at this level of 0 degrees Celsius. So if we consider now part C, we again need to deal with change of temperature, means heating up the water which formed after the ice to water phase transition. So now QC is equal to mass of water. We already have water in our system only, times specific heat of water times change of temperature. And that is 100 degrees Celsius minus 0 degrees Celsius. So we heated up water from 0 degrees Celsius to 100 until we reach this 100 degrees Celsius and some phase transition of water to steam start to happen when water actually started to boil. So that is region D, and QD is defined as latent heat of phase transition water to steam times mass of water, assuming that all water is converted into steam. And also at the end, we have this region E. So that is also associated with specific heat capacitance and change of temperature because we heat up this steam. However, in this case, we need to consider also specific heat capacitance of steam, not of water. So we have mass of steam times specific heat capacitance of steam times delta T. So after considering all this change of temperature versus transferred energy plot for water, we identify different regions on sequence of different regions with changing and constant temperature, means we have regions where we just warm up the matter and regions where we have phase transitions. In particular, we have two regions with phase transitions, ice to water and water to steam. So these obviously have to be taken into account when you consider some systems because you need to know that if your temperature changes in those regions where there are phase transitions, so latent heat obviously has to be taken into account because it will always eat part of this energy pie in order to happen. Otherwise, it will not. This change of the thermodynamic conditions will not happen. So summarizing our discussion today, so we introduced two very important concepts of thermodynamics, means internal energy, which is defined by kinetic energy of translational, rotational, and vibrational motion of any of all atoms which form the body with respect to the stationary reference system originating at the center of mass of this body. So it means that it excludes bulk kinetic energy of the system with respect to some external reference system. Also potential energy of interaction between all these atoms inside the body. And also we introduced heat as transfer of energy across the boundaries of the system due to temperature difference, and considered the units which are used to calculate heat, like energy transfer in calories or joules. Introduced heat capacitance and specific heat capacitance, and latent heat, which are associated with heating up or cooling down the matter, or energy needed to be transferred to carry out the phase transition of this matter. And considered on the explicit example of water. So first ice, cold ice, in the process of transferring external energy to the system, we change this temperature of the ice, we cool it, warm it up, then it reaches temperatures of phase transition. First ice transforms into water, then water into steam, and eventually we can warm up this steam to very high temperatures. And each of these steps which happen with the initial ice, we can quantify amount of heat transferred to make it happen. Then we will proceed further in our discussion already on Monday, when we operate with work. So we will introduce one additional transfer parameter work done by the system, and that will be enough to consider in details define the first law of thermodynamics and consider its applications. Okay, thank you for your attention. If you have any questions, you're welcome. So don't forget, tomorrow midterm. So I wish you good luck, be careful, attentive, read carefully the problems, don't be in a hurry while you're reading. Better read it a few times to avoid unnecessary mistakes. Okay, then, thank you for attention. Have a good day and good luck with your midterm number 3.
Thank you. Goodbye.
Thank you. Goodbye.